Alright, hello again. This is Zachary Kottman with a video on doing our Matlab homework 3. I'm going to focus on parts 1 and 2. Just going to do transfer function and a few other quick things. Nothing crazy. So, alright, I have drawn the system that we are designing a filter for, and the first thing that the homework asks for is the transfer function of this system. And the easiest way to do that is to use the quote-unquote impedance method. And basically the impedance method says that the voltage, because the sum of the voltage around this loop is 0, you have some voltage increase across here, voltage decrease across these, voltage decrease across this, and the voltage seen across this resistor is just equal to the ratio. The voltage seen across this resistor, the ratio of that to the voltage in is the same as the ratio of the impedance across the resistor to the impedance of the capacitor plus the inductor plus the resistor, the total impedance. It's pretty simple. Alright, so let's just get it going real quick. So we're saying the transfer function equals V out over Vn equals, and here let's say this is Z1, Z2, Z3, and we know that the impedance of the resistor is just R, and the sum on the bottom, I'm actually going to rearrange the order a little bit. Z2 is what do we do? R plus LS plus 1 over CS. Z3, Z2, Z1. Cool. Alright, so it doesn't really matter what exactly what form this is in for solving for the roots, except that we want some s squared and terms here, so that we have something like, x squared plus ax plus b, or I guess ax squared plus bx plus c. We want something that looks like that, but with s squared. So in recitation, we just multiply the top and the bottom, the numerator and denominator, by CS, and we end up with RCS over LCS squared plus RCS plus 1. Okay, so no big deal there. We can take this denominator and find the roots, and that's going to get us information that we need about the natural frequency of the system and zeta, the damping ratio, or whatever that thing's called. So we're going to go ahead and do that. But a quick comment, this also looks like you can rewrite this way too, just by bringing the RC back to the denominator. I still want an s squared and an s and stuff here, but this has the same roots as this, even though you moved an RC from the numerator into the denominator. I mean, it's you're just multiplying by a constant. Anyways, it has the same roots. So as long as you have s squared and s, and then a constant here in the bottom, in the denominator, and you solve for the roots, you're going to get the same answer whether the denominator looks like this or like that. Cool. Okay, so anyways, I'll just do this one. It doesn't matter. But we have, you can say the roots are going to be negative RC plus minus square root R squared C squared minus 4LC over 2LC. And that's just from this equation, which everybody knows, roots of a quadratic. Cool. Alright, so we're just going to manipulate this. We're actually wanting to manipulate this to look like, and I forget what we said here, but I'm just going to give it some constant, some constant, plus minus j omega n square root 1 minus square. So this is where I'm going to focus. Like, this is the form we want to see. We want 1 minus something here, and then whatever's out front we know will be j times omega n. So I'm just going to move this stuff around until, massage it until it looks like this. Cool. So we can say this equals negative RC over 2LC plus minus I'm going to divide both of these by a negative 4LC, or multiply and divide by. So pulling a negative 4LC out, I get R squared C squared over negative 4LC plus 1. Do a little simplification. I'm going to pull this outside of the square root, and so I'm going to get a j from the negative, and then a 2 square root. Did I do something wrong? Nope, all good. I still have this 2LC down here. Those 2's are going to cancel. Square root negative, let's put the positive first. 1 minus R squared C squared over 4LC. Alright, and the last simplification, and just because I tend to do this, you couldn't see all that. Pull it up here. Alright, so there we go. And this form, this section looks very much like j omega n. Looks exactly like 1 minus zeta squared. Sweet. So what this means from here is that omega n equals 1 over square root LC, and then zeta squared equals R squared C squared over 4LC. So zeta equals, oh, I should probably just simplify this. There we go. Sweet. You know what? Let's just go for like the quality factor stuff too. So what this will give you in your problem is this equation, since you're given omega n and you're given the inductor, this equation determines your value for the capacitor, Let's see, it looks like squared. It's going to be C equals 1 over omega n squared L. Let's see if that's what I wrote down. Oh, that's off somewhere else. Who cares? That's going to be correct. So, all right, and we also have Q equals 1 over 2 zeta. So that's going to be 1 over R square root L over C. But we also know that this is, oops, the center frequency, or the frequency we want, the natural frequency over the frequency bandwidth. And then we can use this relation. Since we know C now, we know L, we know C, we know this, we can solve this for R. And I will double check my algebra here against what I wrote earlier. Yep. Awesome. Actually, haha. If you substitute this into here, you can just get R without even having the capacitance relation in there. Just say ends up being, because you're given these two quantities, omega n and L, you're definitely starting with those. Well, I guess you're given the Fn. So, anyways, it ends up being 2 pi delta F L. But that's neither here nor there. Alright, that's everything. Thanks for watching.